Hey there students, Mr. Fugue here. In our video today, we're going to be going through a bit of an overview on one of our labs dealing with the smart cards. Specifically, this should be in your notation system, Lab 2C, and our title here, and I'll mention this because different years we may adjust the numbering system just a little bit, but our title here is Don't Be a Smart Mess. Okay. So, our focus in our lab for today is going to be using our smart cards to look at the relationship between mass and acceleration due to gravity. Now, we do have a lab sheet that accompanies the lab here, so we want to make sure you can access Canvas so you can have access to the lab sheet and follow along with where we're going to go. This is going to be one of our design lab activities, and so for this lab, I'm not going to be giving you all a procedure to follow. I'm going to be giving you an objective, an overall goal, and then it's going to be your responsibility to come up with what you'll measure, your procedure, how you'll do your analysis, and then you'll be able to execute your procedure. Now, in this video, we're going to be doing a bit of an overview on the overarching concept of what we're trying to do, and then we'll transition into a sample procedure for those of you that may be working remotely or didn't have a chance to get to do things here in class. So, what we're looking at, as I mentioned, is the relationship between mass and what we call acceleration due to gravity. Specifically, we're going to look at if changing the mass of an object changes the acceleration it experiences due to gravity. Now, at this point in the year, we haven't gotten too far into gravity and gravitational forces just yet. For the most part, we're operating under the belief that gravity is the force that makes things fall toward the ground. Okay? There are a lot more subtleties to that, and we're going to get into those later in the year. But for now, we're looking at gravity as just what causes the force that causes objects to fall. And so we want to try and see if changing an object's mass will change the rate at which it falls toward the ground. So, how are we going to do that? Well, we've got here our smart card setup. Okay? Now, what I'm going to do with that setup is this. Okay? I've got a book here, and I'm going to place that book, set my card over here, under one end of the track. In doing so, that's going to create a bit of an angle, okay, or ramp, if you will. And what we can do now is we can actually let the cart travel down the ramp, and it will go from rest to speeding up some non-zero velocity, so it's going to accelerate. Now, if we take a moment to consider what's causing it to accelerate down the ramp, hopefully we should be able to see that gravity is going to cause the cart to travel down the ramp. Now, gravity is not the only force that's present here, right? The cart is actually on the track, so the track's kind of holding it in place. It's not the same as just dropping the ball straight down, but in an indirect way, okay, well, gravity is causing the acceleration down the ramp. Okay, there are some other forces that are affecting its acceleration, but gravity is the main force that affects it going down the ramp. So what we want to do with our setup is look at the mass of our object, and we can actually change the mass of our object with the smart cards using some of the masses that we have. We'll get into that when we talk about the procedure. And so what we'll do is we'll use those different masses along with our smart card software to check the acceleration of the cart and see if there's a noticeable difference. Toward the end of this lab, what we're going to look to do is we're going to look to generate a graph of acceleration versus mass, and we'll see what that graph tells us about this relationship. Is it the case that increasing the mass, excuse me, is it the case that increasing the mass increases the acceleration? Is it the case that increasing the mass decreases the acceleration? Or is it the case that increasing the mass causes no change in the acceleration? Remember, this is acceleration due to gravity. As we'll later see, the mass of an object does affect its just acceleration it can experience horizontally, that sort of thing. But here we're looking specifically at acceleration due to gravity. So hopefully that gives you kind of a broad overview on what we're going to be doing with the lab. Here in a moment, we're going to transition over and look at what a sample procedure would look like for how to go about executing the lab that we're looking at for today. You do want to make sure, as I mentioned earlier, that you have access to Canvas and the lab sheet so you can follow along with the procedure that we will go through. And then we'll transition over into looking at our procedure and collecting some data to be able to work with. Okay? So we'll transition over to that now. Okay, so now that we have a bit of an overview of what we're trying to do, we're going to talk a little bit through what a sample procedure would look like. So as a reminder, our goal is to look at the relationship of mass and acceleration due to gravity. So what we want to try and do is to change the mass of our object. Our main object here is going to be our smart cards, and to see if changing that mass shows a noticeable change in the acceleration. Specifically, if you look at your lab sheet, which you can find in Canvas, there's a hypothesis that we're trying to check, and that is the relationship of mass to acceleration linear? More specifically, if we were to double the mass of our object, does that double our acceleration? If we were to triple the mass of our object, does that triple our acceleration? That's the type of relationship that we're looking for. So we want to be careful once we have our data analyzed that we look for, is there an actual relationship, or are there maybe just some small fluctuations in our numbers that don't necessarily signal a clear relationship there? So the two things that we're going to need to measure are mass and acceleration. To get mass, I have just one of our regular scales here that we use in the classroom. And what I'll probably go ahead and do is I'll probably go ahead and get my masses after I've done my work with the accelerations. The mass shouldn't be too difficult for us to measure. I should be able to put our objects on the scale and get a reading pretty clearly. I also have our additional masses here that we use with the smart carts. So what we'll be able to do is we'll be able to test the smart cart just empty with no added masses, and then we'll add 1, 2, 3, and 4 masses in here. So what we're looking to do is we're going to measure mass using our scale. We're going to measure acceleration using the smart cart itself. And here in a moment, once we start collecting data, you should see on your screen a bit of what the data looks like, and we'll talk through kind of how to find that using Vernier. And so we should have a pretty direct way to get our two measurements. Remember that acceleration and velocity are oftentimes pretty challenging measurements for us to take, but if we have our smart carts, we have a good way to be able to do that. Without the smart carts, we'll probably have to use kinematics and kinematic equations to find what we're looking for. So what I'm going to do here is I'm going to go ahead and get my setup going, and then we'll start collecting some of our data. You all may not be able to see on the screen, but over here I've got my Chromebook hooked up to my cart. And here in a moment, once we start collecting some of the data, you'll be able to see how we're going to get those accelerations. If you're a little bit unfamiliar with how we're using the smart carts, how they get set up and paired, make sure to check out the smart cart resource video. That's a great resource for how we're using the carts, how to set up the tracks, how the software system works. I'm going to go through this assuming you've seen some of those things before. So if you haven't, make sure to reference that resource page, and that will get you set up with what you need. Okay, so I'm gonna go ahead and take my cart up to the top of the track. And over here on my software system, real quick, what I'm going to do is make a quick adjustment. And I'm going to show this to where we just have one graph. Okay, that'll make my data a little bit easier for me to see. So we'll get things going in 3, 2, 1, collect. Let the cart go down the track. It's the wall, and then I'm going to go ahead and hit stop and bring my cart to a stop. So here for just a moment, I'm going to go over and show you all how we're going to get our data from Vernier. Okay. So what I've got here is my graph is currently showing position versus time. So what I want to do here is I want to click on that position title on the y-axis, and right now I just have one data set collected because I've only run one trial, and I want to turn off the position. I'll hide that. It doesn't mean I'm deleting the data, it just means I'm not showing it on the graph, and I'll click on acceleration. Okay, so let's look at what we've got here. Remember, this is a graph of acceleration versus time. This isn't necessarily showing velocity. Just for comparison's sake, this is our velocity versus time graph. You'll notice the velocity starts very close to 0, and then it increases up until a maximum. This is likely our point just before hitting the wall. And then the cart hits the wall, it momentarily will stop, so its velocity goes down to 0, and then it begins moving in the negative direction, so its velocity is kind of a high negative value, and then it will slow down as it moves back up the track. So what we're concerned with is we're concerned with the region before hitting the wall, where we have a nice constant acceleration. So that's going to be this range right in here, where we see our flat and mostly constant acceleration. Now you'll notice if I click on any of the points in here, it looks like we're seeing about 0.345, 363, 341, 345, 352. So we're seeing accelerations that are all around 0.35, 0.36. So a natural question might be, which acceleration do we use? Should we just grab one and go with it? It may not be very clear which one to get. So one of the better approaches here would actually be if we could take an average of this entire flat line of our constant acceleration. And the smart carts actually have a great way for us to be able to do that. So what I'm going to do here is I'm going to click on the edge of that flat portion, and I'm going to click and drag all the way back here. I'm going to be careful to not get too close to the region where I see my acceleration dropping down. That's the area where we're hitting the wall. Or this region right at the beginning where my hand might have still been on the cart. I want to check out this region where I have a nice constant acceleration. Now down here in the bottom left-hand corner, we've got what's called our graphing options. I'm going to click on that, and it's going to give me a menu of other options. What I want is view statistics. So I'll click on view statistics, and what I'm looking for is this piece of data right here, the mean value of what I'm looking at. Here we're looking at accelerations, so our mean value is an acceleration. My number here is 0.347 meters per second squared. I'm going to make a quick note of that over here. So I've got that value down. So when my cart is empty, this is my mean acceleration, 0.347 meters per second squared. Okay, so what I'm going to do now is I'm going to come back, and now we're going to run our next trial. So I'm going to add one mass to my cart, and again, once I've concluded with this, I'll go ahead and get my masses all together. So now I've got my next mass in, and I'm going to run my next trial. So here we go, 3, 2, 1, go. Okay, I'll go ahead and stop, bring my cart to a rest, and then I can see my nice flat portion of my constant acceleration. I will go ahead and select that region, hit view statistics, and I've got 0.350. Okay, make a note of that. And then, oops, just go ahead and get all of my masses out here. I'll add my next mass. Run collect again. 3, 2, 1, go. Stop, bring the cart to a rest. And same process, I'll get my average acceleration. Select my region, view statistics, and 0.354. Okay, I've got all those saved in my computer, so I won't write them all down right now. I'll come back to them in a moment. Okay, and we'll run our next trial. 3 added masses, 3, 2, 1, collect. Okay, hit stop, bring my cart to a rest, and again get my next average acceleration. And view statistics, 0.353, looking actually relatively close. And then our last trial with 4 added masses, and 3, 2, 1, collect. And stop. Okay, and then I'll see my last acceleration here. And view statistics. Okay, 0.357. Now, a question you all may be asking is, why did we only test the acceleration with the masses one time? Something we've emphasized a lot throughout the year is the importance of multiple measurements. Now here, I am taking multiple overall measurements. I'm checking the acceleration at my 5 different masses, empty, 1 added mass, 2 added masses, and so on. But I'm not going through multiple trials at each measurement. Why am I not doing that? Well, I want you to consider the labs in which we've gone through multiple trials of the same measurement. Consider, for example, the marble launcher lab we did where we were checking angle and distance. In that experiment, what we saw was whenever we launched the marble at a certain angle, the performance wasn't consistent. Sometimes, for example, we'd launch at 30 degrees, the marble would travel 75 centimeters, then 85, then 72, then 68. So there was a very wide range of what our system was doing, and so we needed to get a consistent idea of what was happening, so we measured that multiple times because we didn't have a whole lot of certainty on what our points were. As well, consider the Fall in Love with Gravity lab that we did, right? Where we were dropping an object, taking some measurements, and then using those to try and calculate for acceleration due to gravity. There, in that lab, what we had to do was we had to drop the object multiple times because we were recording the air time, how long it took the object to reach the ground. And when we are recording things like time, there's going to be a good amount of inaccuracy because of our reaction time. Sometimes we're not too good at starting and stopping exactly when we need to. And so in those experiments, we went through the same trial multiple times, hopefully so that we can minimize any error that we're making with one specific measurement. But with our smart carts, we're not really having to do a lot of guesswork on what our numbers are. The masses here, we should have a lot of confidence with. I'm going to put those on the scale here in just a moment. And the accelerations are all coming from the smart cart itself. And these carts actually give us generally really good data. And so it's actually not really necessary for me to have to let this go down the track multiple times at each mass because the smart cart software is giving me a very reliable number for what I'm doing. Now, is it bad practice for me to do this maybe twice and take an average for each mass? Not a bad practice at all. But given that I have a system here and some equipment that's very accurate with what it's reading, we're not going to require you all to take a lot of measurements when we're using things like the smart carts and trialing them over and over and over and over and over again. Okay? Now again, is it good practice to always get more measurements? Sure, but given what we have here, we should be pretty solid with the measurements that we've got. So what we're going to do now is transition back over to looking at some of our data analysis, and we'll show us and we'll take a moment to look over how our numbers look and draw our conclusions on what's going on with mass and acceleration. Okay, so now that we've collected our data for what we're doing here with our lab, I've gone ahead and input that data into a spreadsheet here on Google Sheets. So you'll notice I have a column here for my acceleration values. Remember, I found these just from using the Vernier software, and I went ahead and collected my masses for each of the different trials and put them into my column over here. So I have my data for acceleration and my data for mass. Now, just by looking at the numbers, it doesn't appear that there's a very clear trend. My points don't seem to be consistently increasing or consistently decreasing. In fact, they actually all seem to be relatively close to about 0.35, but sometimes we want to make a graph so that we can better see what's going on with that trend. So I'm going to go ahead and click on all of my data points here. You can grab the title if you want. That's just going to input. In fact, I'm going to go ahead and avoid the title just for now. I can go ahead and add that in later. I'm going to hit Insert and Chart. And now, it actually has mass on the y-axis, acceleration on the x. We wanted a graph of acceleration versus mass. So I'm going to go ahead and adjust that over here on my chart editor, where it says x-axis. I'll remove those points. And I want the acceleration there. So I'm going to grab my values from column A. On the right, over here for series, I'll hit Remove. Oh no, I'm sorry, I wanted acceleration versus mass. On the x-axis, I want mass, which is column B. My apologies. On the y-axis, I want acceleration, which is column A. Okay, so now I can see here that I have a relatively consistent relationship, meaning, what I mean by consistent, to be more specific, is I can clearly see that increasing the mass does not show a linear increase in my acceleration. I'll go over here to series. I'll add in a bit of a trend line just so I can see. My trend appears to be mostly that as I increase the acceleration, I see no noticeable change. Sorry, as I increase the mass, I have no noticeable change in my acceleration. One thing I do want to do here is go ahead and adjust my titles, meters per second squared, just so I know exactly what we're looking at. And on the x-axis, I have mass in grams. I can also tell because if I look at my data points down here, these are all in the 3 to 700 range, which are my masses. On the y-axis, those go to about 0.4, which are my accelerations. So I'll go ahead and adjust that. Acceleration versus, I'll leave the units off in my title here. That way I can just see I'm graphing acceleration versus mass. There we go. And I can see that there appears to not be a linear relationship between acceleration and mass. Now remember, this is specifically acceleration due to gravity. As we've talked about, gravity isn't the only thing affecting the cart's acceleration, but it is affecting the cart's acceleration down the ramp. Now, one part of our lab does ask to adjust so that we can see the origin. So you'll notice here on the vertical axis, I can go down to 0, 0, or I can go down to acceleration of 0. On the horizontal axis, I'm going to scroll over here. My min value of 0, I'm going to put my max out to about 800, just so I can have all of my points here. That way I can clearly see where 0, 0 is. I want to make sure I have my graph scaled without any breaks. That way I'm not as likely to misinterpret what I'm seeing here. So this would be the final product that we're looking for. We can see our graph of acceleration versus mass shows that as I increase the acceleration, there does not appear to be a linear increase in our mass. And more specifically, to address back to our hypothesis, our goal was to check and see if doubling the mass doubled the acceleration. Here I've got a mass of about 289. If I double that, I'd be around 560. And so at 289 to 540, I'm relatively close to a double. And look at my acceleration. 0.347 to 0.355. That is clearly not a doubling of the acceleration. A doubling would be somewhere around 0.65 or 0.7. I can triple my mass approximately from 289 to 786. Not an exact triple, but relatively close. And there I see that my acceleration increases slightly, but it's not a tripling. A tripling of my acceleration would be well over 1 meter per second squared. So this is a good example of when we're analyzing our data, we want to make sure that we're not allowing these very small fluctuations to cause us to misinterpret what we're seeing. Here,
changing our mass does not show a linear change in our acceleration. And that is what our goal was that was what we set out to try and figure out, was does the mass have an impact on our acceleration due to gravity? So our conclusion here is that it does not. So hopefully this gets us set up with everything we need for Lab 2C. If you were not able to complete things in class, hopefully you've now been able to see what our lab looked like and draw the important conclusions that we need to see. If you have any questions, you're always welcome to reach out to your instructor, and please let me know if you need any help with what you're working on. Other than that, good luck.